Here's a recording of the Q&A session for lecture number 5. As usual, I've edited out the students, and we've tried to repeat their questions. Sometimes you'll see me pop up in order to repeat a question that we forgot to repeat in the live session. Here we go.
So the question was about what's going on with the environment diagram of print sums from lecture. So here's the example. I think I may have changed the name of the inner function a little bit, but it does the same thing. And yeah, what happens when we start with just print sums of 1? Well, print sums, even though it has a def within a def, it all gets executed in one step. We just create the print sums function. The fact that it has inner stuff doesn't really come into play until after you call it. And when we call it, we print, and then we create a new function. So what's interesting here is that this new function we create has parent f1, which means it knows about n. The parent frame is this same f1 as this f1. Basically tells you that the body of f can refer to anything that's in this f1 frame. So when we look at the body of f, which print sums n plus k, we don't know what k is yet, right? That's what f will get when it gets called. We do know what n is 1. And this returns this function called f of k. When you write return f, that looks up what value is bound to f, turns out it's a function, and that's the return value for this whole thing. So what happens when we extend this? Well, one way we could extend this is to capture that result in a name and then call that 3, let's say. And we could give that a different name, and we could call that. So this picture gets slightly more involved. Everything was the same up to the point where we returned. When we return, this return value is now bound to the name G in the global frame. Why in the global frame? Because this assignment statement, J equals print sums of 1, was a global assignment statement. It's not invented. It's not part of the body of a function. And so G gets bound in the global frame. But what it gets bound to is the function that was created in the local frame. So it has this local parent. Now we have a name for it. We call it on 3. What we're calling is this f function. When we call it, we have to construct its frame correctly. That means giving it the correct name, not so important. Giving it the correct parent, really important. Giving it the correct names and values, also really important. So k is bound to this 3 that we passed in, but it also knows about n equals 1. So when we execute its body, which just says return print sums n plus k, we're going to add these two numbers together, 1 and 3, before we call print sums. So we're going to get the number 4, and then we're going to call print sums. Where is print sums? It's not in this frame. It's not in this frame. Oh, there it is in the global frame. It's just this function. Okay, so when we call print sums, we're calling it on 4 because we computed that before we called it. And now it's going to print, because that's the first thing that it does. It will print the 4, and it will create a new f function. Same code, different parent, therefore different value of n. And that's kind of the whole point of this example, is that we're summing up things as we go by always keeping track of the sum so far in this name n in a print sums frame. But every time we call this f, we're making a new print sums frame with a new value for n.
So let me emphasize here one thing about the environment. So prior to these examples, we had basically the function frame and the global frame. And it was pretty straightforward. You look for things in the local frame, and if you didn't find it, you go in the global frame, and you're done. And it seemed like an overly complex formalism for just that simple thing. But now, when you have functions within functions, you really see the importance of these environment frames to keep track of what the variables are bound to.
Yeah, so, and one of the things that's interesting about environment diagrams is that every time you call print sums, you get a different frame. Every time you execute the body of print sums, you're executing this def statement, def f, again. And so you're getting a new f function, same code, but different parent, which means basically a different n each time. Okay, so if we walk forward a little bit more, we're going to return that, and it will get bound where? To h in the global frame. So now we have a way to refer to this f where its n is 4. which is 1 plus 3. So if we want 1 plus 3 plus 5, well, we already have 1 and 3 together. It's right there. It's n equals 4. And so we can add 5 to that by calling this function, which was originally called f, but in the global frame is called h. So we call h on 5, introduces a new f frame, whose parent is f3. f3 is the one that has the sum so far. That's n equals 4. Here we call print sums on 4 plus 5 is 9. That's 1 plus 3 plus 5 is 9. And that gets printed out.
And John, maybe now you can go back to the original one where you wrote print sums of 1, 3, 5, and just we can explain why those are exactly the same.
Yeah, so if you look at this picture, we have global names for G and H. It turns out that we could avoid those. Instead of saying, give this result a name and then call it by name, we could just call it directly. So this thing was briefly called G in our former example, but now we're just calling it print sums 1. And likewise, instead of calling this H, we could, and then calling H, we could just call it directly. And I believe this is the example that was in the lecture. We're going to see the same behavior up here, 149. We're actually going to see exactly the same thing down here. All the names, all the parents, everything is identical. Nothing changes. The only thing that changed when we switched to this version is that we don't have the global names G and H and W anymore because we're not giving these intermediate functions names. Instead, we're just calling them right away. So the question was, why does this end up having a return value of f instead of a return value of print sums? Because it says print sums right here. It's a good question. The reason is that we're not just writing print sums. We're writing a call expression that evaluates something. Whatever print sums returns is going to be the value of this whole call expression. And that's what will get returned from f. So this says f returns whatever print sums returns, which turns out to be another f function. So in this sense, it says f is going to return an f. And that's what we see eventually in f2. This f call returns an f. Now, it doesn't actually return the same function that was called to make this. That was this one. It returns a new f. And what's different is the n value is different because the parent is different. So if this example had been slightly different and we had written that, then the first call to f would have returned print sums. But since we called it, we get another f that gets returned instead.
Yeah, this is a really important distinction is on line 4 right now, you're not returning a function, you're returning a value that is the result of evaluating a function. In line 5, you're returning the function. And let me just state the obvious, but just to make sure, you're also, that def statement that starts on line 3, that function doesn't get a value, right? You're just defining a function. Yeah, so that return on line 4, that's just part of the body of that internal function. And then, of course, you return that f. That is what gets returned from the print sums.
The question was actually about a midterm question, but I think we've narrowed down to the essence of what was going on. And we'll try to answer a few questions along the way. So kind of why does the environment diagram for this look the way it does? Here we're defining a function, which actually depends on y, even though y isn't defined yet. That's okay, because when you execute the def statement, you don't really do anything with the body yet. You just kind of squirrel it away in there. It's part of this function, but we haven't tried to execute it. So the fact that we assign y later is fine. When we call f of 2, x is bound to 2, and then it starts assigning things. So me is bound to 1. We assign a g to some function. If we change me now, then it's changed in the F1 frame, which means that if we were to call g at this point, let's say on 7, the value of me that it would use, since there's no me here, we look in the parent, is actually 2. So this would return 2 instead of 1. Even though me was 1 when this was created, the fact that it got changed later does affect the behavior of G. And so 2 is going to get printed out. And then this can return x plus y, where we look in here and we find the x. We look in here for the y, but it's not there, so we look in the global frame. So you do have to be conscious of the fact that assignment can change the binding between names and values in an existing frame, and that affects all the functions that were created with that frame as the parent. I think maybe one more question that was in here is, what about the order of names within a frame? And it really doesn't matter. The order of frames does tell you something. That tells you what was called first and what was called second. But the order of names within a frame, you could think of it as just kind of a grab bag of names. And so if you saw on some example that this was like X me G instead of X G me, that's the same.
Yeah, that ordering, I think that was your question, right, Austin? That ordering there is not the order of evaluation, but as John just said, the order of the frames really matters. But once you're in an environment, you can only have, every variable can only have one value. And so it doesn't matter what order you put them in. There's no precedence there that you have to worry about.
The next question was, what is currying and what does it do?
So let me give a high-level explanation of it, and then John's going to bring up an example. So what currying does is it takes a function that takes more than one parameter, 2, 3, 4, 5, whatever, and it converts it into a function, a series of functions that each take only one parameter. Yeah. So that's the sort of the high-level description of it. Take a function with multiple parameters, f of x, y, and turn it into a series of functions that take g followed by an h followed by whatever, okay? So let's take a look at that now, and then we'll make sure we understand it.
Yeah, so here's a definition that only works for functions of 2 arguments. You could imagine writing one that takes an arbitrary number of arguments, but it requires a little bit more effort. So we'll focus on this one for now. And, you know, the point is to take a function that already exists and kind of change how you call it. It doesn't change the behavior of the function. Like when I curry pow, pow is that function that raises one number to the power of the other. I don't actually have like some new mathematical ability, but what I do have the ability to do is bundle together the function, the pow, with its first argument by, for example, calling curried pow on 2. So now I have a function where whenever I call it, it will raise 2 to that power. So 2 to the power of 5 should be 32. And we'll make sure this works, and then we'll talk about why it's useful. Yeah, okay, so x got to be 32. Sometimes when you have a function that takes 2 arguments and you're writing a long program, you know the first argument early, and you don't really know the second argument for a long time. And so it's convenient to be able to give a name to the function with its first argument filled in already. You can do this explicitly every time. Like if you could, I could have, instead of calling curry2, I could have written 2 to the y returns pow to y. Currying just lets you write it in a more compact way. You could just say, I want to curry to pow, and then I want to fill in the first value as 2.
So John said it really nicely there. You can think about the power of currying as the ability to sort of almost like halfway evaluate, right? So the function here, 2 to the, is very specific. You don't have to pass multiple parameters. And again, it's important to understand this gives you no real new mathematical powers, right? There's nothing that you can't do with the full function. It's sometimes just convenient to only have to pass in a single parameter and specify the other parameter sort of in a fixed way. And somebody asked in the chat, is this similar to giving a default value in the def statement? And the answer is sort of yeah.
Yeah.
It is. If we had defined POW with X being by default 2, then you could just call it with one parameter, and that was the default. The only difference, it's slightly different in terms of functionality, but conceptually that is the same idea.
And in your Hog project, you see a lot of these examples where you know some things early and you don't know some things later. So it shows up in the strategy functions, where the strategy kind of takes in some facts about the strategy. This is like at question 10 and 11. Like, what's my cutoff for rolling 0 instead of rolling 5 dice or whatever? And like, that's one input. But then the rest of the inputs are what the actual scores are in the game. And you don't know those until you're playing the game. So you can fill in some of the values that you need to do the computation before you even start playing to kind of set up your strategy. But then the rest of the values don't come until you're in the middle of the game and you start rolling dice.
And somebody's asking about the name curry2 in the chat, and that's just an arbitrary name. John just called it that because it's a curried function, but he could have called that Z or my name. Good.
Yeah, so the reason I call it curry2 is that curry is the like computer science name for this thing. And the 2 was to say that F has 2 arguments. Yeah, great question. So the question's about this slide from lecture and why the make getter frame comes before the compose one frame. When you look at the code, it seems like compose one is getting called right away. Turns out it's not. So here's the detailed rule for evaluating a call expression, is that you evaluate the name compose one. So you do know you're going to call compose one, but you don't call it yet until you know what you're going to call it on. So you need the function that you're going to call and its arguments before you can draw the frame. So for this reason, we know we're going to call compose one, but until we've evaluated square and make getter 2, we don't actually make the call to compose one. And this is just how Python works, but it's a pretty natural way for it to work because, you know, it doesn't know whether calling make getter 2 is going to take forever. It might have an error in it. Who knows? So it doesn't actually create the compose one frame and start executing the body of compose one until after the arguments are determined. And to determine the arguments, you have to evaluate square. Well, that's quick. That's a name lookup. But this is a call expression, and so that's why this frame comes first.
Got it. So just to clarify, for that specific line, it needs to call the arguments first, square and make adder, before it actually calls compose one.
I would say you have to evaluate. You have to know what the actual parameters are. Yeah. So if I call a function with 2 and 4, then that function is ready to go. I know what the values of the parameters are. But in this case, that the first parameter is fine. Just the name of a function, nothing to do. Notice there's no parens there. I'm not calling the function. I'm passing the function name as a parameter. But the second one is a function call. So I've got to go off and evaluate that. I need to know what I'm passing in. Once I know what I'm passing in, I can create the frame, find the formal parameters, and then start evaluating.
Exactly. And like, yeah, for anyone else who's still kind of wondering about this, the simplest possible example would be if F adds X and Y together. You don't call F until you know what X and Y are. So if you have some other function that adds 1 to things, and you call F of 2 and G of 3, you don't actually call F until you know you're adding 2 and 4 together. And for that reason, you see the G frame first. Yeah, great question. So if you have, I'm going to show you a simpler example of the same thing, I think, which is here we're going to compute Y equals F of 3. So what is this going to do? Well, F adds 1 to things, so we're going to add 1 to get 4, add 1 to get 5, add 1 to get 6. When you visualize the execution, you see F1, F2, and F3 all appearing, unless you change the way this environment diagram is displayed to only show you what you need, at which point, well, let me just do it from the beginning. it will create the F1 frame. When you return from this F1 frame, you really don't need the frame anymore. That's why we gray it out. But in this version, where you change that option, it actually just disappears. So that's why F1 and F2 and F3 aren't there, is that, you know, sometimes when I run Python tutor, I don't display exited functions. Now, I recommend just displaying them all the time, because then you can really see everything that happens. And yeah, so when we talk about it in discussion or exams or whatever, we just kind of show the whole thing. But sometimes that's unreasonable, you know, like if you want to see what happens with something really big, sometimes the best way to visualize something like that is to not display it, and then you can kind of see the progress of this going from 4 to 5 to 6 to 7 to 8 to 9. There is a little issue, kind of technical issue, that I guess I'll make people aware of, which is that if you just go to pythontutor.com, then you get a version where the default is to hide exited frames as opposed to showing them all. Whereas if you go to tutor.cs618.org, you go straight to a version that says, yes, show all the exited frames. So that's what I try to use consistently, but clearly in video 3 of today, I forgot to do that. And so that's why some of the frames disappeared. Yeah, so the question is, if you have two inner functions, so they have the same parent frame, can they somehow refer to each other's formal parameters? So could, for example, h, which can refer to z and can refer to x, could it somehow refer to y as well? And the answer is no, and maybe for a good reason. When you call h, there really isn't a y. Like, in order to get this far, there must have been an x, right? Because f has to be called for you to get here. And there has to be a z. We gave the z right there, 7. But there kind of isn't a value for y at this point. So these names and these names can't really interact in any way, and you can't look up one from the other.
So that's exactly right, of course. And by the way, that's true whether those were embedded in F or just not embedded all in the global frame. You'd have the same problem. Now let me ask a follow-up question. If in G, John, I assigned the variable a to be 1, can I use that, and we can go back to embedding that within the def x, but is that accessible? Sorry, I shouldn't have had you.
No, we got to
I can find another local variable there. Now the question is, can I access that inside of H? And the answer is no also. The scope of that parameter is G. H doesn't get access to it.
Exactly. So the only way you could get access to A, you could use it directly, or you could use it within a function that's in here.
Right.
You could talk about A, but you can't do anything with it from the outside unless it's returned.
Right.
So the question is, what's going on in this lab example? This is from lab 2, question 1, where there's a function that takes f, returns a function that takes x, and then calls f on x. Now we have a function that takes x and squares it. What would it be like to call higher order lambda on 2 and then g? So when you call higher order lambda on 2, you are calling a function that takes an f. And you can kind of peek ahead and see, what is it going to do with this f? It's going to call it. But passing in 2 for this is going to give you a problem eventually. And that problem is you're going to try to call 2. So it would be as if you were saying something like f equals 2, and then I call f on 3. This will give you an error which says f is not something you can call because it's a number. Yeah, so what else happens here after we've created a function that's going to call 2 on something is we pass in the thing that it's going to call 2 on, which is g. So g refers to a function that squares. That will be our value for x. So another way to look at this is to say x equals g. That would be kind of like, there's basically two ways to do assignment. You can use assignment statements, or you can pass values into functions. So this would bind f to 2, and this call would bind x to g, or I could just write it out explicitly like this. And then if I call f of x, I kind of run into trouble. So let me just comment these out and show the behavior if we wrote this function, this set of lines, and then we'll see that basically the same thing's happening in that example. So here, this creates a function that squares, this creates a number, so f is 2, x is this, and we're just calling it the wrong way around. So we're getting this int object is not callable. If instead we had called the function on the number, we would have gotten 4. We kind of did it the wrong way around.
By the way, I find that so offensive, calling the function name x and the parameter f. It's sort of like there's a part of my brain that is exploding looking at that.
Right.
Call x2, knock that off. Stop calling x2.
Exactly. So this is why, interpreters don't care, but you have to write code.
Yeah, I know. Only Honey cares.
Humans can understand, exactly. So if we look at this, here we call this function, which takes f. It's bound f to 2. It's done that thing that's so offensive, using f as a name for a number. And what we get back is the result of evaluating lambda x colon f of x. That's why we get another lambda function. Even though this one says line 1 and this one says line 1, these are different functions. This one returns lambda x f of x. This one just returns f of x. So when we call that, we just called this one. We bound x to what we passed in, g. And then it tries to do the work of calling the number 2 on the function that squares, and that's wrong.
Yeah, the lambdas can be, especially those embedded lambdas, can be a little hard to follow. Again, remember, when you see lambda, you're defining a function. The next thing is this is the parameter that will be passed in, and everything after the colon is a return statement. That's all you can do in Python in lambda expressions. So whenever you see it, say that to yourself. It helps a little bit. That's a function. It takes this parameter, and it returns this.
Yeah, you could even translate it and make your life easier.
Yeah, and don't try to parse the lambda within the lambda. Just say it returns this. Okay, what does it return? It's a function that takes a parameter and returns this thing. Yeah, so it's good to sort of tease those things apart a little bit. And by the way, what John is doing now is you can always rewrite them as defs. Right? The only difference between the lambdas and the defs is that the lambdas are anonymous functions. You're not explicitly giving it a name. So a good exercise is to rewrite them with defs, and sometimes those are a little bit easier to parse and understand. Yeah, and then you give them explicit names so you can see them clearly in the environment variables, environment diagram.
We'll like slap this up here, and now we'd see the same error, same environment diagram. The question is, in the Lambda video, there was some discussion of intrinsic names and that being the only difference between a def statement and a Lambda expression, and what's an intrinsic name. And really all it is the name you see right there when you try to display a function, and you get these carets and like some mystery thing which you can ignore until 61C. And but you do see a name. Even if we gave new name to this, it would still be the f function. So that is the intrinsic name. It's a very unimportant part of the function, but it does exist. So that's why I just mentioned that there is this slight difference. If you had written, f equals lambda x plus 1 and looked at f, this wouldn't be f anymore. It would be lambda.
The next question was again about currying. Is currying just a design decision? Is it helpful in any particular case? And how does it get used in practice?
You want to give that a shot?
Well, I'll give my take on it, and John may have a different opinion on this, which probably tells you, well, that's probably true of most things, by the way. I think it's a little bit of a design issue. I think but I think also it really is about sort of whether you want to bundle up a fraction of a function call because you're going to be reusing it over and over and over again. So again, I just want to emphasize, you don't have to do it. I don't know that there is an advantage computationally or even frankly organizationally. I can imagine a scenario where it's nice to name, like the way John did earlier with, power of 2. It's nice to name that because just from the readability of the code, instead of looking at the parameters and trying to figure out you're raising something to the power 2, it's sort of in the function name. I have to say, I don't know that I've ever used currying functions in the many, many decades I've been coding. But maybe John has a different perspective on it.
Yeah, I mean, currying, whether you write currying as a function or whether you write out the explicit syntax of, like I have an f that takes 2 arguments and I want to make a new g that just takes the first argument and gives me back a way of calling f on that first argument and some second one that I don't know yet. So you could write this, or you could write curry f, and you'd kind of get the same thing. They're both currying. I mean, one, there's like a function for it, and one, you're sort of writing some code that does it, but you're doing the same thing in both cases, which is that you're splitting up when you get x and when you get y, so you can get one and not have the other yet. If you're just writing a whole program by yourself, I don't think this comes up so often. But there are lots of cases where you're using somebody else's code. So somebody else has written a function that takes 4 arguments. And you kind of want to set 2 of the arguments, the first 2 arguments already. And then you kind of use the result many times in your program. And so you would want to kind of build a new function of 2 arguments with the other 2 already filled in. And that means that people can write very general libraries where they have functions that take tons of arguments, and then you can specialize it sort of on the fly. And this does show up fairly often. So this concept of bundling together a function and some of its arguments into a new function that takes fewer arguments, which is really what currying is all about, that's a pretty useful technique for organizing programs.
Yeah. I can also imagine a situation, I may have to bend over backwards to do this, where you have to actually do some work with the first parameter. Computationally, you have to do some calculation. And if you're calling that full function over and over and over again with both parameters, you're going to do that work over and over and over again. And maybe you want to do that work once, bundle it up, and then send it off. So I could imagine a computational benefit for bundling that up, just by the way, depending on the specifics of the function.
So here was an example that a student found on the resources tab, and the question was for step 4, why didn't lambda get called? How come there's no lambda frame? Instead, what we see is that there's a lambda function, which is some value, bound to grounds. Why did it come out that way? It came out that way because when you evaluate a lambda expression, every time what happens is that you create a lambda function. You don't call it unless you have parentheses after it. So if you ever have a lambda function and then you call it right away, you'll see a lambda frame. But if you just give it a name, then you won't see a lambda frame until later when this function actually gets called. And in this case, instead of giving it a name by assignment, we're giving it a name by passing it in as the argument to another function. So we're creating a function, that's what evaluating the lambda expression does, and then passing that function in as the argument to coffee. Coffee is getting called because coffee has parentheses after it. So we create a coffee frame where this lambda function that we just made is the argument. And what do you do with arguments? Well, you just bind them to their names. So now we have a local name, grounds, for this function. If at some point we call grounds, which we do down here, we'll see the lambda frame. But until we call grounds, really the only way to refer to this lambda function is by grounds, and if it doesn't get called, then we'll never see a lambda for you. So maybe I can say that more succinctly.
Yeah. So let me
yeah, maybe how you can
let me just try to summarize, and we'll see if this answers the question. Is the parameter being sent to ground is an actual function definition. I'm not evaluating that function. And the only time I create a frame is when I evaluate a function. If I'm just passing a parameter, I simply bind the parameter and I send it off, and that function has to do what it has to do. Yeah.
So let me show you one variant on this, which is almost the same. Let's just define this function, give it the name f,
Good.
and then call coffee on f. No parentheses here, just f. There, this line creates the function and gives it a name. And then we're still not calling f. We're just referring to f by passing it in as an argument to the coffee function. At which point, really all that does is give another name to this function. But it doesn't call it yet. It doesn't get called until we see a call expression with either f as the operator or grounds as the operator.
Yeah, so really important when you see function names is to look afterwards. If there are parentheses where you're passing a parameter, or even if they're empty parentheses, you're calling the function. If they're not, you're simply referring to the name of the function, either to assign it to a variable or to pass it as a parameter. And it's really important, you know, code is super particular. And so that just that difference of the parentheses makes a huge difference, right? Whether you're evaluating the function or assigning it or passing it as a parameter. So you have to read very carefully, and you'll get in the habit when you see functions of always looking for those parens to tell you whether it's being called or not.
Well, great questions today, folks.
Good. All right, everybody, it's 10 o'clock. We have a long weekend. I hope everybody gets a little bit of rest, a little bit of time off, and we'll pick it up again. I guess we don't have this on Monday. Is that right, John?
That's right. No lecture for Monday, so no Q&A on Monday, but we'll be back on Wednesday.
See everybody Wednesday. Have a great weekend, everybody. Thank you.